So the definition for a reduced row echelon form, it is in row echelon form. In the row echelon form, I suppose we should have the definition for that too. That's the zeros in the bottom. So let's prepend the definition we have with this one. So matrix is in row echelon form if it satisfies the following properties, and it says that if you have any rows that consist entirely of zeros, they're all the way at the bottom. We don't want them in the middle or on top. And in each non-zero row, the first non-zero entry is called the leading entry, is in a column to the left of any leading entries below it. So what this says is that you would have numbers. Let's do one with 4 rows, and let's imagine that the bottom row is full of zeros. So if you have any rows with zeros in it, it would be in the bottom. In each non-zero row, the first non-zero entry is in a column to the left of any leading entries below it. So if the second row has a leading entry here, then it's in a column whose leading entry is below that. Yeah, the stars are non-zero numbers. If you had something that's all zeros, then it would be there. There's some cases where it won't be all zeros, in which case you don't have any zero rows. Does that make sense?
2 numbers far at the right on the bottom, that would still be.
Say it again?
So those 2 at the far right could be numbers and that.
Yeah, so these things could be non-zero here also. Or I'll do this.
If it is all zero, does that mean no solution?
No.
It just
It
means 0.
just means 0. Yeah, 0 is equal to 0. If you had a number, and if this was an augmented matrix, and then you had a non-zero equal to 0, then it would be an issue. So this is the row echelon form. It basically has some sort of staircase property, and it doesn't have to be exactly at each step. As you can see, like the second row has 2 zeros instead of 1 0, and then as long as it goes down like that, then it's in row echelon form. So a reduced row echelon form has added properties to something like this, and the added property is that the leading entry in each row is 1. So you can reduce it by just dividing things out. Each column containing a leading entry of 1 has zeros everywhere else. So each column containing a leading 1 has zeros everywhere else. But that means that all the other places may not necessarily be 0. So it's possible to have non-zero, non-1 equal on those other places where the leading column doesn't have, the column with a leading 1 doesn't have, it's possible that the rest of them is non-zero or not 1. Okay, so that's a reduced row echelon, and you know, computers are nice tools to help us find these things. And so how do you go about doing this? You basically row reduce like we've done before, and then you just make sure that you divide out the leading terms so that you have a leading term of 1 for each row. And that's called using this to solve for a system of linear equations is called Gauss-Jordan Elimination. And if you like step-by-step processes, step 1, write the augmented matrix for the system. Step 2, use elementary row operations to reduce into row echelon. And then step 3, if the resulting system is consistent, solve for the leading variable in terms of any remaining free variables. So we talked about leading variables and free variables. So let's use this example and imagine our situation here. These things with a non-zero, with the ones in it, would be the leading variables. And then if this came from a system, then this would be an augmented matrix. And then we would have a couple of free variables. And those free variables will be represented by parameters when we're expressing our solution. So I'm pointing to the column because each column is represented, or can be thought of as being represented by one of those variables, right? So if you had UV VW XYZ or something like that, or X1, X2, X3, then those are the variables that we're talking about. And we did an example in class. I don't know if I was going to do another homework problem, but the homework problem I was going to do was the same one that we had last time. So maybe I'll do a slightly different homework assignment. Like this one. So this one is a little simpler because it only has 2 equations, but it has 3 unknowns, which makes it a little bit interesting. I guess I should have copied, I should have not, oops. Should have taken that out. Anyways, so if you had 2 equations, then you'd write them out and write them out on top of each other, and then you can see better the augmented matrix result. So let's get the augmented matrix going here. 4, 1, -1, and 0 for the first one. 2, -1, 3, and 4 for the second one. So clearly it's not in row echelon form, so let's try to get it in row echelon form, or let's do reduced row echelon form. And we can do this in a variety of ways, but in the end, your reduced row echelon form should be unique, which means if I do it a certain way and you do it a certain way, when we compare answers for our reduced row echelon form, we should have the same thing. If it's not a reduced row echelon form, we still might have different answers, but the reduced row echelon form should be the same. So I'm going to do a switch first. So I'm going to switch the first row, the two rows. Victor?
So when you reduce echelon form, where are the zeros?
The zeros, I should expect this to be 0, and if there are more zeros there, then I would expect them to be 0 here, here, and anywhere. I would not expect this to be 0, the first one. The 4 should not, that spot over here should not be 0. And this spot here should definitely be 0, and then whether the others are 0 or not depends on the system. So I'm going to do a switch first. I'm going to switch row 1 and row 2 because I can. 2, 1, oops, 2, -1, 3, and 4. 4, 1, -1, and 0. And then I'm going to multiply the first row by -2 and add it to the second row. So R2 plus -2 R1 replaces R2, which means R1 doesn't change. And this is going to be 0, which is what I was shooting for. And then whatever else happens, if the rest are zeros, then it's really up to how the system is supposed to work. So if I multiply the first one by -2, this becomes +2, add 1, so that becomes a 3. Multiply this by -2, this becomes a -6. Add to -1 is +5. Wait, -7. And then if I multiply this by -2, that's -8. Add it to 0, it's just -8. So at this point, I can think that I'm done if I just want it in reduced, row echelon form. But we can take it a step farther and have it in reduced row echelon form by taking the first row and then dividing it or multiplying it by 1/2 and then replacing that first row. And I could take the second row and multiply it by 1/3 and then replace that second row. So if I take that one extra step, then I would be in reduced row echelon form. So divide by 1/2, I get 1, I get -1, -1/2, and I get 3/2, and 2, divide by 3, -7/3, -8/3. So is this in a reduced row echelon form? Oh yeah, there's one more thing. What else do we need to do? So this -1/2, according to reduced row echelon form, I have to try to wipe anything else above any row that has a leading coefficient or has a leading variable. So this has a leading variable here, the second row, and it means that second column for the first row has to be 0 as well. So I'll just do one more step. And so for R1, we're going to multiply the second row by +1/2 and then add that to R1 and then replace R1. And because the first column of the second row is 0, that's not going to do anything to the first column of the first row. And we did this move to get this -1/2 gone, so that's 0 now. Now the rest is a bunch of tedious arithmetic. -7/6 plus 3/2 -2/6. Did I do that right? I'm trying to do fractions in my head, and that really hurts. plus 2/6. So we can change that into a third. And then I would, okay, let's erase it and change it to a third. Negative 8/6. Negative 8 plus 12 is positive 4, 6, 2/3, 2/3. Oof. All right, so now is it reduced row echelon? So this is in reduced row echelon form, and if I were to plug this into Mathematica or MATLAB, then I should get, if I plug the original matrix into Mathematica or MATLAB, I should get the same thing. Okay? All right. So let's see if we can answer this question. Find the line of intersection for the given planes. So these are two planes in three dimensions, and they intersect in a line. So if we solve for this, we should be able to come up with a solution. Simon?
So the term above the leading coefficients has to be 0?
Yes, it has to be zeros also. If I have a leading coefficient somewhere, the term or terms above and below it, if you have a bigger matrix, they need to be zeros. Above and below. All of them above. All of them below. We only have 2 rows here, so it's hard to visualize that, but everything else above and below has to be 0. Well, everything below is 0 because that's row echelon. But now everything above, if there's more rows above, then everything above will be zeros. All right. Now, if we can write this, let's use the reduced row echelon form to see if, what we can find out about this system. We have, we're using x, y's, and z's. So this is x, 1x plus 0y plus 1/3 z is equal to 2/3. We have 0x plus y minus 7/3 z is equal to negative 8/3. Oh, by the way, let's do some, we didn't talk about rank yet, but before we talk about rank, let me ask you, how many variables do we have? So we are in R3 with 3 variables. How many leading variables do we have? How many non-zero rows do we have? How many 0 rows do we have? How many free variables do we have? How many? 1. So leading variables are x and y, and z is a free variable. Yeah. I don't know. Yeah, we'll have to see how that works out. Say it again? We want x to equal t.
Yeah.
So they're forcing you to have this to be 1, so that x is equal to t. You should be, but I guess if they force you like this, you might have to do it. Well, let's walk through this and see if I can find a solution, and we'll see how that compares and fits into their answer. So, if my free variable is z, I'll have that, which according to this will be an issue already because z is equal to 2 plus whatever. So let's finish the way I have it set up over here. So that's the free variable. Then I have x is equal to 2/3 minus 1/3 t over 3. And then my y is going to be negative 8/3 plus 7/3 t. So that solution is going to look like, or should look like this, should look like what color? So your x, y, z is going to equal to, x is going to equal to 2/3 plus t times negative 1/3. Y is going to be equal to negative 8/3 plus t times 7/3. And then z is going to be equal to 0 plus 1. Now, what do you know about lines in space? It's a point in a direction. I've found a point here in a direction, right? Now, if my line and their line is supposed to be the same, so I should be able to do this with any scalar multiple, provided that their point is on the line, which it should be. Otherwise, then they must have done something wrong. So can you guys visualize this? Let's see if we can visualize it. Say it again. Multiply the which last term? That's the thing, is that I shouldn't have to do anything.
That's the right one to pick, right?
Because it's the direction, right? So here's the visual. Let's see if we can get a visual of this. So their point is 0, 2, 2. And my point is not so nice, but it's 2/3, negative 8/3, 0. And the graph is supposed to be passing through this point, or these 2 points. So my direction vector might be going this way. But regardless of whether it's going this way or the other way, it has to be on the line. And so this is a vector negative 1/3, 7/3, and 1. In fact, I can multiply this by 3 and have a direction vector that's 3 times as long. It would still work. And maybe the vector they're looking for, if you'd switch the free variables around, would be going this way, whatever that direction vector is. And it shouldn't matter. So if I use their point and then use my vector, it should still create the same line. If I take my vector and do a scalar multiple of that, it should still create the same line. So what I'm proposing is that I type in this answer and it should be correct. Let's see what happens. This is kind of exciting. My initial point is different, but that shouldn't matter because it's still the same line. And the direction that I have should be a scalar multiple of theirs. So should I submit or should I just assume that it's correct? So if I would have taken my vector and multiplied by negative 3 so that it would be positive 1, negative 7, and negative 3, I should still get the correct answer because in this case, the direction of the vector doesn't matter because it's going to describe your line in regardless. There's a lot of things that would have been nice to know. All right. So that's finding the intersection of planes. It's really putting a system of equations together. What else did I want to do? Oh, let's actually talk about rank now, which is an important concept that we'll come back to over and over again. So the first one is a definition, the second one's a theorem. So the definition of rank of a matrix is, this definition is based on doing a row echelon form reduction. And the rank of a matrix is the number of non-zero rows in a row echelon form. And so there's going to be a lot of ways, this is one of those things that we're going to keep coming back to. There's going to be a lot of ways for us to figure out the rank of a system of linear equations. And the first way we're looking at is through the matrix after you do the row reduction. So after you do the row reduction, you know a little bit about the number of free variables you have, the number of variables you have in whatever space that you're in. And so this is another way to look at that. The rank is equal to the number of, it's actually equal to n minus the number of free variables. So if you just solve for rank A, this is how you would find the rank. Or the way they have it written, if you do a row reduction, you can anticipate the number of free variables that you should have based on the rank and the number of original variables you have. Okay. So the number of free variables in the future will have a better name, a more mathematical name to that, and it'll be based on the spaces that we're studying. It'll be called the null space later on in the future. All right. So I think we're done with this section. Let's see if there's any more to talk about in this section. Oh, yeah. They introduce homogeneous kind of out of the blue, and then they talk about finite fields. So I'm going to mention homogeneous out of the blue, and then do some examples of finite fields. So just to throw some more definitions at you. And don't get this mixed up with the homogeneous and differential equations. If you're taking differential equations, that's a homogeneous equation is different, or function. A linear system is called homogeneous if the constant terms are all equal to 0. So in other words, if you have your augmented matrix, and then all the numbers on the right side of that dotted line that you would draw is all equal to 0, then we have a homogeneous system. And the theorem says a homogeneous system of m linear equations with n variables. If you have more variables, then the system has infinitely many solutions. Do we need visuals for this, or? Yeah, have you guys seen this notation too? The square brackets and then matrix. Yeah, it's right here. Now you've seen it. Let's do a simple example, and maybe I won't go through the whole thing. 2x plus 3y plus 5z. Oh, you know what? Sorry. Are you guys writing this down? I'm going to just copy the example that we had earlier. Oh, but this is not homogeneous. Ugh. Crap. Yeah. Yeah, let's do that. Thanks. Oops, I can't erase. Anyways, so if the last column, if I have a couple of equations of planes that have zeros, then they would all intersect at the origin. And so if I were to write this as a system or as a matrix, we get 4, 1, -1, 0, 2, -1, 3, and 0. So this system is homogeneous. And then according to this theorem, if you have m linear equations with n variables, if you have more equations than unknowns, then you're guaranteed to have a solution. In fact, you'll have infinitely many solutions. More, oh, if I have more variables than equations, or less equations. So let's rephrase this. If we had m is the number of equations. If you have less equations than variables, then you have infinitely many solutions. So in this case, this has infinitely many solutions. So by the way, in this notation, I don't know if I talked about this notation much, and I don't know if you've gone through the HBA already, but the HBA assumes that there's some sort of vector multiplication business happening there. And what happens is that the matrix A that's not augmented is the matrix 4, 1, -1, 2, -1, 3. And then the zero matrix, it's not the zero matrix, but the zero vector that they're talking about here is a vector with zeros in it. And we haven't talked about matrix multiplication, but if we let x equal to xyz, in this case, since we are in R3 and we have three variables that we're talking about, a times x is equal to 0 is a matrix vector way of writing this system. And what this is equivalent to is you take your matrix A, 4, 1, -1, 2, -1, 3, and then you so-called multiply it by x via this thing called matrix multiplication, then you should get your vector 0. Well, let's write it as a vector 0, 0. And we'll dive into this matrix multiplication and more properties about matrices in the next chapter. So this is just like a little preview of something that you're kind of working on in your HBAs that's related to what we're doing. All this stuff is related, and we're going to come back and do different things that does the same thing that we're doing now. Maybe a little bit easier, maybe a little bit more difficult, but just different. And they're all going to culminate in this idea of studying rank and null space and vector space. Okay, questions? Let's move on to what? Finite fields. Oops. So for finite fields, really the only thing I can think about doing is an example. So there's some examples that I picked out from the book. Let's do number 55 to start off with. And what this is really is the same thing that we've been doing, except you just have to adjust your arithmetic. And it's really just arithmetic that we need to worry about. And so when you say subtract, you really have to add something, add its negative. And when you say multiply or when you say divide, you really have to to work with the multiplicative inverse. So it might be good, especially with these finite fields, it might be good to have the addition and multiplication table handy. So if you want, this would be a good thing to have. We're in Z3. So we have our addition table. 1 plus 1 is 2, 1 plus 2 is 3, but in Z3 you're back to 0. And then 2 plus 1 plus 2 is 3, again that's 0. And then 2 plus 2 is 4, mod 3 is 1. So this is your addition table. And your multiplication table is, should be kind of similar. And anything times 0 is 0, 1 times anything is anything, and then so the only thing you need to worry about is figure out what 2 times 2 is. That's the same thing as 2 plus 2. 2 times 2 is 4, which is 1 mod 3. So what's important here is that you have inverses. Then that'll help you to check the body of the table to do subtraction for the plus, and then check the body of the table to do division for multiplication. I think I said that backwards. Anyways, so let's get started with our system. Let's write our system in matrix form. And this has 3 variables. It has 3 equations. And whoops, 0? Thank you. So 0, 1, 1, and 1, 0, 1. So here is our augmented matrix. So now we just have to be careful about how we do our multiplication. So I am very interested in getting rid of this 1 down here in the 3rd row in the first column. So I'm going to do something in my 3rd row. I'm going to add something from my 1st row being multiplied by something to add to 1. So I need to make this into a 0. So what do I add to 1? What do I add to 1 to get 0? So I need to add 2 to 1 to get 0. So I'm going to multiply the 1st row by 2 and then add it to the 3rd row and then replace my 3rd row with that. Yes, it gets confusing. That's why it'd be good to have your finite brain going. I don't know. That's why it's also handy to have your multiplication addition tables. We have our multiplication addition tables memorized, and we know how to do subtraction and division fairly well, right, in our heads. But subtraction and division for finite fields is a different story, and that's why having this table and knowing how to use it would be good. All right, so it looks like I'm not going to change the 1st row. I'm not going to change the 2nd row. I'm focused on the 3rd row, and then you have to be careful again. So 2 times 1 is 2. 2 plus 1 is 0. So 2 times the 1st row, right? So I need 2. Messed you up, huh? 2 times 1 is 2. 2 plus 1 is 0. So that's where this one comes from, and that's where this one comes from. The next one will become 2, I think. So 2 times 1 is 2, plus 0 is 2. Just don't say this out loud in the STEM Center. People might think you're weird. Actually, say it out loud in the STEM Center. So 2 times 0 is 0 added to 1, so that doesn't change. And then here is a 1 and a 1 combination again. So 2 times 1 is 2, plus 1 is 0. So that's our first step. Now let's yeah, but yeah. So we want to solve for this. We want to get a solution. So we wanted to reduce row echelon form. Okay, so we have 1 here. We have 2 here. So we want to get rid of this 2. So the question is, so I still want to work on R3. And the question is, what do we multiply R2 by to get rid of this 2? Just 1. And then 1 plus 2 is 0. All right, so I'm not going to change my first row. I'm not going to change my second row. And now 0 times whatever, that's just 0. 1 times 1 is 2. No. 1 times 1 is 1, plus 2 is 3, which is 0 in our finite field right now. 1 times 1 is 1, plus 1 is 2, and this is just a 0. So we can finish this off and make it reduced row echelon, or we can just rewrite it back to our system and then back solve. I think I'd rather do that right now. I think we are going to get a solution. Well, let's see. Remember, this is a finite field, so that's something strange also happening. Let's see, x plus y plus 0z is equal to 1. Y plus z is equal to 0. And 2z is equal to 0. So, the question here is, what do I multiply 2 by to get 0? What do I multiply 2 by to get 0? 0. So z has to equal to 0. So if z is equal to 0, I can back solve. Y plus 0 is equal to 0, so y is equal to and then continue to finish back solving. You have x plus y was equal to 0 is equal to 1. So what does x equal to? So what's my vector solution? 1, 0, 0. Guess you write it however they want it written. But it looks like that's going to be our solution. Oh, I didn't pick it from the homework set, so I don't have a chance to check. There's 1 over z2. Oh, you guys can work with that. Okay, so with finite fields, you're doing the same thing, except you have to be careful about how you think about subtracting and dividing. Because in these fields, you can only multiply, add and multiply. And so this idea of multiplicative inverse and additive inverse becomes a lot more important. Okay? All right. I think that's good for that section. Spanning sets and linear independence. So let's go to section 2.3 now. So 2.3 starts off with a theorem. A theorem says a system of linear equations with an augmented matrix is consistent if and only if B is a linear combination of columns of A. What does that mean? First of all, what's consistent mean? Has a solution, has at least one, could be more, could be one. Really, our choices are either one solution or infinite number of solutions, right? If it's consistent, right. Or no solutions, that's our third option. So let's see if we can take a look at a sample problem. First, we have to talk about what a linear combination is. Yeah. So do you know what a linear combination is? Why didn't I define that first? Sorry, I'm looking at my notes. Here's the definition. No, that's a span. Oh boy. I have to make up a definition. Let's see, before we do this problem, what is a linear combination? A vector B is a linear combination of vectors. Now, to be abstract, they usually have like arbitrary n vectors. So that's what I'll do. U1, comma, U2, comma, UN. So a vector B is a linear combination of vectors U1 through UN if there exists scalars I usually use alpha, I think. Alpha 1, alpha 2, alpha n, such that the vector B that you're looking at is equal to alpha 1, that's a scalar, times the vector U1 plus alpha 2, another scalar, times the vector U2 plus, and so on until you get to alpha n times the vector Un. So that's the definition of linear combination. Basically, if you can write the vector as some scalars times each of the other vectors that you're talking about, then it's a linear combination. For example, if we'll try to write V as a linear combination of U1 and U2, oops. Maybe I'll put U1 and U2 here first. So I should be able to find alpha 1 and alpha 2 to satisfy this equation. So vector v is 1, 2, 3. Alpha 1 is something I need to solve for. 1, 1, 0. Alpha 2 is another thing I have to solve for. 0, 1, 1. And if I can find alpha 1 and alpha 2 such that this is true, then I can say that V is a linear combination of U1 and U2. Now, how do you suppose we do this? Guess? I suppose we can guess. Yeah, we can see if we can make this into an augmented matrix. I really want to keep this on the same page, but I'm getting a little long on the page here. Let's transform this into a matrix equation. Or first, let's transform this into a system and see how it looks like. It looks like I have alpha 1 plus 0 alpha 2 is equal to 1. Did you see how I got that? I just went through alpha 1 times 1 plus alpha 2 times 0 is equal to 1, just on the first components. Now for the second component, I'll have alpha 1 times 1, alpha 2 times 1, so alpha 1 plus alpha 2 is equal to 2. And then I would have alpha 1 times 0, alpha 2 times 1 is equal to 3. Okay? Now, right below this vector equation, I'm going to write our system as an augmented matrix. So the augmented matrix will become 1, 0, and 1. One, 1, and 2, 1, 0, 1, and 3. So that's my augmented matrix. So the theorem, maybe we should have done this before explaining the theorem, but the theorem says a system of linear equations with augmented matrix A is equal, A with the B attached to it, is consistent if and only if B is a linear combination of the columns of A. So B, 1, 2, 3, is a linear combination of the columns of A. So that's exactly the same thing, right? So if we can find a solution for this, then that means V must be linearly dependent. It's a linear combination of U1 and U2. All right, let's do it. Let's row reduce this. We should get a row full of zeros here, I think. Let's see. I would take row 1. It always gets confusing the way they write it. I want to change row 2, so I will add -1 times row 1 and then replace row 2. Oops. 1, 0, 1. So I'm going to do 2 steps here. Actually, I'm just going to do 1. So this would be 0, this would be 1, and this would be 1. Is that correct? I would, but technically I'd have to do it on the next row because I just had changed row 2, so it doesn't quite. So I'll do this one where what Victor said, row 3 plus negative row 2 changes row 3. So the first row doesn't change, the second row doesn't change, and the third row becomes 0, 0, 2. Uh-oh, now what? So what does this say? This says that no solution. So this says that alpha 1 equals 1, alpha 2 equals 1, and 0 is equal to 2. Right? So this, we finally run into a problem where we have no solution. So in terms of the language that they have, is this consistent or inconsistent? Inconsistent. So if this is inconsistent, then we can't ever find alpha 1 and alpha 2 that would make this equal to 1, 2, 3. So our conclusion here is no solution for alpha 1 and alpha 2. Therefore, V is not or cannot be written as a linear combination of U1 and U2. So there's some cool graphics that's associated with this whole business about linear combinations if we stay in 2 and 3D. Just to give you a little preview of what we can do next time, is that if you have this point 1, 2, 3, you have a vector 1, 1, 0, and you have another vector 0, 1, 1, then these two vectors, if you found linear combinations of them, what am I drawing? What does this look like I'm drawing? It looks like a plane. So what I'm trying to draw here is a plane. And what happens is that if this point is on the plane, then I can get to that point by scalar multiplying these things and adding them and eventually get to this point. But if this point is not on the plane, then there's no way I can find these scalars to make me get to that point. So this point is not on the plane. So we can see if we can find more visuals tomorrow if I use like graphing calculator or Mathematica. All right, that's it for today. Tomorrow or next time on Wednesday, you guys will have a quiz on systems, and one of those systems will be a finite system.